compressed air engines are quietly re-entering the automotive conversation, and this time they are being framed as a serious zero-emission alternative. While electric vehicles dominate headlines and internal combustion engines slowly fade, another technology is resurfacing from history with the potential to reshape how we think about mobility. Imagine a vehicle that runs without gasoline, diesel, or lithium batteries. No tailpipe emissions, no rare earth mining, and no fuel costs tied to volatile global markets. Instead, it uses something endlessly available. This idea may sound futuristic, but in reality, it has been around for more than a century. The concept of compressed air engines dates back to the 19th century, during the Second Industrial Revolution. Engineers at the time were already exploring mechanical energy storage as an alternative to burning fuel. One of the earliest examples was the Marari system, which used compressed air expanded through a piston to generate motion. What made the Marari system particularly innovative was its use of heat recovery. After expanding, the air was reheated using a hot water tank before re-entering the engine. This improved efficiency and extended range. Because of its reliability and lack of emissions, the system found practical use in trams and mining locomotives, environments where ventilation and safety were critical. Despite its promise, compressed air technology was eventually abandoned. Fossil fuels were cheap, powerful, and easy to store. Gasoline and diesel engines quickly took over, pushing alternative systems into obscurity for much of the 20th century. Interest in compressed air engines returned in the early 2000s as environmental concerns and energy security became global priorities. Automakers began looking for alternatives to both fossil fuels and battery-heavy electric vehicles. Around the early 2010s, companies like Peugeot revisited compressed air technology with renewed seriousness. Peugeot developed experimental hybrid vehicles, most notably a prototype version of the Peugeot 208. This car combined a traditional gasoline engine with a compressed air system. The results were impressive. The hybrid system achieved efficiency figures equivalent to roughly 141 miles per gallon. The idea was simple but clever. Compressed air powered the vehicle during acceleration and low-speed driving, while the gasoline engine took over at cruising speeds. This reduced fuel consumption, emissions, and wear on the engine. It also allowed the vehicle to recharge its air tanks through braking and surplus engine power. The compressed air system included a high-pressure tank under the trunk, a low-pressure chamber near the rear axle, and a hydraulic unit in the engine bay. Together, these components allowed for fast air recovery and smooth transitions between power sources. Although these vehicles never reached mass production, they proved that compressed air engines were technically viable. They also attracted interest from other major manufacturers, including General Motors. Modern compressed air engines have advanced far beyond their early designs. Unlike the single-stage systems of the past, today's engines use piston-driven mechanisms capable of operating at high revolutions per minute. Springs control piston movement, and modern air heaters replace older water-based systems, improving consistency and efficiency. To start the engine, a small electric motor is used. This motor acts as both a starter and an alternator, initiating motion until the compressed air system takes over. From an engineering standpoint, the design is elegant and surprisingly simple. However, despite their appeal, compressed air engines face major challenges. The most serious issue is efficiency. Compressing, storing, and expanding air leads to significant energy losses. As a result, real-world range remains extremely limited. Most compressed air vehicles would struggle to exceed about 80 miles on a full tank. That range is not practical for most drivers, even for daily commuting. Long trips become nearly impossible without frequent refills. Refilling itself presents another problem. Unlike electric vehicles that can recharge through regenerative braking, compressed air tanks require time and specialized equipment. While air is abundant, compressing it to usable pressures is energy-intensive and slow. Power output is another limitation. Pressurized air has very low energy density compared to gasoline or modern batteries. This results in weak torque and limited performance. Compressed air vehicles cannot match the acceleration or pulling power of electric or turbocharged engines. Because of this, compressed air engines must operate at high RPMs to compensate. This creates additional challenges, especially when it comes to lubrication. Introducing lubricants into an air-based system is complex, increasing wear and reducing engine lifespan. Maintenance costs could quickly erase any upfront savings, making the technology less appealing to consumers. Safety concerns also exist. High-pressure air tanks can be dangerous if damaged. However, similar risks exist in electric vehicles and gas-powered cars, and engineering solutions have reduced those dangers over time. It is worth remembering that electric vehicles faced many of these same criticisms only a decade ago. Through continuous development, they improved rapidly. Compressed air technology could follow a similar path if investment and research continue. Several solutions are already being explored. High-pressure tanks could improve energy density and power output. Integrating air storage into the vehicle's chassis could increase both safety and range. Materials like carbon fiber offer excellent strength and weight savings, but their cost remains too high for mass-market vehicles. As a result, manufacturers are considering thermoplastics as a more affordable alternative. The growing interest in compressed air engines is reinforced by the number of companies experimenting with them. An Australian firm called Engineer developed a rotary compressed air engine known as the D-Pro motor. It has already been used in boats and industrial vehicles and could potentially be adapted for cars. Inventor Armando Ragazzi patented his own compressed air engine in the 1990s. His prototype vehicle reportedly achieved a range of about 60 miles. Remarkably, it was built with limited resources, suggesting that industrial-scale development could yield far better results. So, will compressed air engines ever reach widespread adoption? The answer is uncertain. If progress continues, limited use could appear by 2030, especially in urban or industrial applications. Automakers are under increasing pressure to move away from fossil fuels and lithium-ion batteries, both of which carry significant environmental and geopolitical costs. Hydrogen fuel cells, such as those developed by Toyota, represent one alternative, even though they have not yet achieved mainstream success. Using air as a propellant would be even more radical. Air requires no mining, no chemical processing, and costs almost nothing. In theory, it is the cleanest fuel imaginable. However, powerful industries benefit enormously from oil and lithium. A shift toward a nearly free energy source would threaten established revenue streams. History shows that energy transitions are rarely smooth or uncontested. While companies like Stellantis and General Motors have expressed interest in compressed air engines, real-world progress remains slow. Similar patterns can be seen with sodium batteries, which offer ecological and cost advantages but receive limited attention due to lower profitability. Despite these obstacles, innovation continues. Manufacturers like Toyota continue exploring hydrogen and ammonia engines, signaling that the search for alternatives is far from over. Compressed air engines may not replace electric vehicles tomorrow, but they represent a reminder that the future of transportation is not settled. As technology evolves and priorities shift, what once seemed impractical may become essential. And when that happens, air itself could become the fuel that changes everything.